Hi everyone, welcome to Physics 2. So this semester we'll be looking into Volume 2 of University Physics by OpenStax. We will start from Chapter 1 of this Volume 2, and at the end of the semester we'll be also looking into the last couple chapters in Volume 1 and as well as a few chapters in Volume 3. All right, so let's get started. The first topics of this semester will be on thermodynamics. We'll be starting with temperature and heat. Temperature is something that we are very familiar with. Even you are a kid, you know that when you were a kid, you know what temperature is for, right? Typically, it's used to describe how cold or how hot the weather will be for a particular day. And you can use different thermometers to measure temperatures. um, So the one I just showed you on the previous page, you probably have used in chemistry lab, and you might have seen something like this, which the thermometer, the needle of it is attached to something made of a coil like this. It's made of by metal strip. So this strip is made of two pieces of different metals. As temperature increases or decreases, the metals, they expand differently in length. So then for the one that is expanding less than the other one, you will then pull the whole strip to that side in this case. So that's how this thermometer works. Now, temperature in physics is defined as high value of something with hot object and low value of it with cold object. So that's called temperature. The symbol for temperature, the quantity temperature is T, capital T, and the SI unit for temperature is Kelvin. It's not the Fahrenheit that you are more familiar with or the Celsius that you are less familiar with. Neither of those two, but it's actually in Kelvin. These days, you probably are using the digital thermometers, which would measure temperature more conveniently. So typically, a digital thermometer would have both settings, Fahrenheit and Celsius. You can actually switch from one to the other. So if you are traveling to another country, it actually will be very convenient for you. Okay, but let's say if you forget to bring a thermometer with you because you think you are going to travel abroad, right? You will enjoy it. You wouldn't think about like in the case you are getting sick, right? So then in that case, how would you convert the temperatures from the ones you are familiar with in Fahrenheit to Celsius or the other way around? So pretty much in everywhere else, temperatures are reported in Celsius. So I told you about this when I first came into the States. In August, the temperatures, the weather forecast says tomorrow is going to be 80 degrees, right? I was like, oh no, 80 degrees. I have never experienced such a high temperature, but it's actually in Fahrenheit. So it's actually a pretty comfortable temperature if you convert it into Celsius that I'm more familiar with. So let's say, how are you going to convert temperatures from one scale to another scale, right? So by now, you know there's Fahrenheit, there's Celsius, and there's a Kelvin. So three different scales. Um, from Fahrenheit to Celsius, the difference in Fahrenheit, 9 degrees in Fahrenheit is corresponding to 5 degrees in Celsius. Now, between Celsius and Kelvin, they are the same. So 5 degrees in Celsius is also 5 degrees in Kelvin, but they are starting from different numbers, right? So 0 Kelvin is minus 273.15 Celsius. And 100 Celsius, it's actually 373.15 Kelvins, okay? Celsius and Fahrenheit, they have different starting point as well. So, but we can use certain reference points. Um, so, for example, for freezing of water, it happens at 32 degree Fahrenheit, right? Under normal conditions, ambient conditions, I should say. But it happens at 0 Celsius degrees Celsius. And water boils at 212 Fahrenheit. It boils at 100 Celsius in under ambient conditions. So if we use those two conditions, then we'll be able to actually convert the number, or we can actually write a conversion factor or conversion formula for that. Let's see how that is done. Okay, so I'm going to stop sharing for right now, and I'm going to switch my camera so I can show you how this will be done in a piece of paper. So let's say you want to convert from Celsius, right? You are traveling abroad, and you want to convert it into Fahrenheit. So you'll write a formula of temperature in Fahrenheit that is related to the temperature in Celsius. So luckily this is linear. So linear means this is just a multiplier, right, of that. So let's say this is A plus B, okay? And A and B are constant numbers, multipliers and constant numbers. So we know that water freezes at 32 degrees Fahrenheit, right? And at 0 degrees Celsius, okay? Now, water boils at 212 degrees Fahrenheit and 100 degrees Celsius, okay? So then we can use those two references, use the numbers, right? So we can say, okay, so this is the equation, and we are going to try to figure out what's A and B. So then we can always convert whatever temperature in Celsius to temperature in Fahrenheit. Okay, so let's say use the first reference. You can write 32 degrees Fahrenheit, right? Equals A is the unknown that we are trying to solve for times 0 degrees Celsius, right? Plus B. Okay. So that's the first condition. Now the second condition, when water boils, it boils at 212 degrees Fahrenheit, but 100 degrees Celsius, okay, and plus B. So use the two references. Now we have the two equations, right? And we are looking for two unknowns, A and B. So now 0 times A is going to be 0, right? So this goes to 0. Okay, so that tells you B is equal to 32, right? So we get that directly, B equal to 32 degrees Fahrenheit. All right, now once we have that B, you take it to the second equation, right? So then you say, all right, so 212 Fahrenheit is equal to A times 100 degrees Celsius plus B, which is 32 degrees Fahrenheit, right? So now move this guy to the other side of the equation. That means you do 212 minus, right? Minus 32 degrees Fahrenheit. That will give you actually 180 degrees Fahrenheit equals to A times 100 degrees Celsius. All right. Solving for A, you divide both sides by 100, right? Divide by 100, divide by 100. Okay. So this then will give you the common factor here will be 20. So that gives you 9/5. Okay. So your A then is equal to 9/5 degrees Fahrenheit, right? Divided by Celsius, as you divide both sides by 100 Celsius. Okay, so divided by Celsius plus or times temperature in Celsius plus B, which is 32 degrees Fahrenheit. So this would be this. This is not A. Sorry about that. This will give you temperature in Fahrenheit. Okay, temperature in Fahrenheit then equals to a factor 9/5 degree Fahrenheit over degree Celsius times TC, temperature in Celsius, plus 32, okay, Fahrenheit. So if you just ignore the degrees, then TF equals to whatever TC is times 9/5 plus 32. Okay, so that will give you the conversion factor, and then you can put the degree Fahrenheit back. All right. Now let's get back to the PowerPoint side. Okay. So using the two scales, you will be able to actually find the conversion equation or conversion factor by going from Celsius to Fahrenheit. You can do the same thing if you are looking for degree Celsius by from the number of degrees Fahrenheit given. So you can work this backwards. Now just treat this as TC, solve for TC in terms of TF. Okay, or you can start with the two reference. In that case, you'll actually so you'll start with again the two references. You'll start with writing now. You're converting temperature in Fahrenheit, right? Back to temperature in Celsius. You're going to say this is A now times that plus B, okay? Or if you don't want that, you don't want to be confused with what you did before, you can say this is C, right? Plus, and then this will be D. So C times C, TC equal to C times CF plus D. Again, use the two references. Now this time, T temperature in Celsius for water freezing start at 0 equals to now C times, right, 32 Fahrenheit, right, plus D, that's your first equation. The second equation would be 100 degrees Celsius, right, equals to C times, now it happens at 212 degrees Celsius plus D, all right? Then use these two equations, you can solve for your C and D. So then you have C and D. Then take them back to this equation. You have your conversion factor of calculating temperatures in Celsius from temperatures given in Fahrenheit. Okay. You probably will see people write the symbols for temperatures differently. So some people in textbook, I think you're going to see just degrees Celsius in this way. So put a 0 as a superscript and then C, or a 0 as superscript and then F. Now in writing, some people may prefer to write in this way. So C first with subscript, because sometimes when you write numbers, say 10 degrees, right? And you might be writing like this. So people might be mistaking it as, mistaking it as 100 C, right? So to avoid that, some people might be just writing as 10 degree and then put this guy over here. But that's just something to keep in mind. Okay, when you see this, then that's what it means. Okay, all right. So the same way you can do the conversion factor, you can work out your conversion factor from Fahrenheit to Kelvin, or Kelvin to Fahrenheit, and then Celsius to Kelvin and Kelvin to Celsius. Okay, so the conversion factor to get the temperature in Celsius from Fahrenheit is this guy. Okay, so you solve for that, and then you kind of solve for C. So C is this guy, and then D will be that guy. So it will be 160 minus over 9, minus of that, or minus 160 over 9 in that sense. Okay, and let's see, do I have, yeah. So this is I think what I want to show you this first. So if you are looking for converting temperatures from one scale to another, you can look them up here, and then you can just use one of these equations. Okay. From Kelvin to Celsius, so basically, or Celsius to Kelvin, so basically you add 273.15 to the temperature in Celsius, that gives you the temperature in Kelvin. The other way around, from Kelvin to Celsius, you actually will subtract 273.15 to get temperature in Celsius. Okay. We will take a look at one example first. Okay. So this one says lowest temperature on Earth. Okay. So official record for lowest temperature ever recorded on Earth was set at Vostok, Antarctica on July 21st, 1983, the temperature on that day fell to minus 89.2 degrees Celsius, well below the temperature of dry ice, which is about 44.7, minus 44 degrees Celsius. It's asking you what's the temperature in Fahrenheit. Okay, so the known here is temperature in Celsius, right? Minus 89.2. So we'll just write that down. TC. And just give me 1 second. I will then stop sharing. So we'll bring this window larger. And it's looking for TF. Okay, so we are converting from TC to TF. So you'll check one of these equations. You're going from TC to TF. So this guy. So the first one. So the equation to write down will be, okay, TF equal to 9/5 times TC plus 32. Okay, so simply that is minus 89.2. And then you take that times minus 89.2 times this guy plus 32. Okay, that will give you temperature in Fahrenheit, which will be about minus 129 degrees. So kind of straightforward on that one. Okay, so this is this guy. All right, and then when you are watching this on your own, you can always pause and walk through what you're before looking at the solution here. You can pause and then solve for it just to get yourself additional practice and then compare to what I got here. Okay. All right. So let's go back to the lecture slides. All right. So that was the lowest temperature on Earth ever recorded, minus 129 Fahrenheit. Now you probably heard about like temperatures on the higher end, like the stars could have thousands degrees Celsius of temperature, even hundreds of thousands, millions of thousands. It seems there's no limit on the high end for temperature, but there's actually a low limit for the temperature. So that is called absolute zero temperature. Okay, so this is referring to the scale of Kelvin. So 0 Kelvin is absolute zero temperature. And that is the lowest temperature in theory one could have, okay, in the universe. Now, converting that to Celsius will be minus 273.15 degrees Celsius, okay? So this can be actually, this is the first one of the thermometers ever used was called the gas thermometer. So it basically works like something like this picture shows. Okay, so there's mercury field in here in this part of the pipe, and then connecting with this flexible tube, and then on this tube as well. So the difference on the levels of the mercury surfaces here indicates what will be the temperature, because temperature of the gas in this bottle over here enclosed is proportional to pressure. Later on, we'll know that we'll look at the microscopic view of it, why that's the case. But for right now, you just need to know the temperature of the gas is proportional to the pressure. So if you can measure the pressure, then you know the temperature of this guy. And for different gases here, you actually, for different temperature of gases, you might get different the pressures that you can measure. Okay, so you're measuring pressure, but you're getting temperatures out of it. So if you use different gases and the response is P temperature temperature T and pressure P, they are linear. So if you use one gas versus other gases, right, you get 4. Let's say if you did this, you got 4 experiments, and you measure their temperatures, and then if you measure their pressures in response to the temperatures, because the temperatures can be changed by changing the bath, the temperature of the bath. Okay, so you got those 4 curves. Now, if you back extrapolated the 4 curves, you will find that they will all come to one point. Okay, so in Celsius, this is minus 273.15 degrees. Okay, so this is called the absolute zero. So this is in Kelvin is the 0 in Kelvin. So minus 273.15 Celsius is 0 in Kelvin. All right, so that's how you can find the absolute zero temperature. And I have shown this to you before. So in case you are looking for converting one temperature to another, from one scale to another scale, then you use one of these, okay? Now let's take a look on a second practice problem here, or example here. So this one says normal body temperatures of our body is 98.6. It's asking you what's then the temperatures in degrees Celsius and what's the temperature in Kelvin. Okay, so again, we'll write down the known givens. This is the temperature in Fahrenheit given. Okay, so T of F equals to 98.6. It's asking you what will be the temperature in Celsius and temperature in Kelvin. All right, so you're going to go back and find those 2 equations that you would need. So this guy for part A, because you're given TF, you're looking for TC, okay? And then once you have that TC, you can use this guy, all right? So I will not go through the solution here, but I'll just give you guys the final answers for these 2, okay? So it's a pretty easy practice for you guys to do that. So the first one, A, will be 37 degrees Celsius, okay? And the second one in Kelvin, this is going to be about 310 in Kelvin, okay? So A, 37 degrees Celsius is the answer, and then B, 310 Kelvins is the answer, all right? All right, now let's move on to the next section of this chapter about thermal expansion. I think we all know that as temperature increases, the materials actually will expand. And then as temperature decreases, actually it will shrink, okay? So we have known this for a long time, and we actually have applied this in our daily life. So if you ever see a bridge, there's joints like this. This is used to prevent the expansion of the material of the concrete due to temperature increases, and then also the when it's cold, it will shrink. The material, the concrete will shrink. So this is kind of acting like a buffer to that. Okay, so any materials will actually the length will change according to temperature change. Okay, and then pretty much most of them is linear, and there's just a few exceptions. Okay, but for most of them, change of length is proportional to the change in temperature. So with a constant. So this constant number depends on what material you have. Okay, so delta L equal to the constant times delta T. And if you do ratio of delta L, the expansion in length of the material divided by the original length of it is equal to a coefficient, we call it alpha, times change of temperature T. And if you rearrange this term, you get this alpha equal to delta L over L, and then further divided by delta T. So this coefficient alpha is called coefficient of linear expansion. Okay, so you expand material to expand in one dimension, and you actually also will expand in a second dimension. Okay, so which we'll talk about in a few moments. But linear expansion alpha is proportional to the expansion length divided by original length divided by the temperature. Okay. So alpha has a SI unit of Kelvin minus inverse because delta L will be in meters, L will be in meters. So those two cancel. Delta T will be in kelvins or in degrees Celsius because Kelvin and degrees Celsius, the increment of temperatures, they are the same. 5-degree increment in Kelvin is also 5-degree increment in Celsius. So these two, either this one or that one, okay, referring to delta T. So alpha, if temperature change is small, then you take a limit of it. So then that means you are doing derivative, right? Derivative of L over dt divided by L. So 1 over L, derivative of L over dt in that case, all right? And now the coefficient of linear expansion does not necessarily be a constant. Typically it's a constant for a certain temperature range. Okay, so like a normal temperature range. Now, when it gets to very low or very high, then it tends to become nonlinear. So in that case, then you'll use the definition of the taking the limit of delta t goes to 0. So then that might be varying. Okay, so alpha might be changing, but if not otherwise stated, we will treat this as a constant. Okay. Different materials have different linear coefficient of expansion. Okay, so metals tend to expand more than other materials. So you see this on top here, they are metals, and then concrete, that's non-metals, and then glass, quartz, they tend to expand less than the metals. Okay, so if you are solving for a problem, if the coefficient of expansion is not given, you can actually look it up here, okay, in this table. Application of thermal expansion. So one of the example you have seen before, so it's this by metal strip for thermometers, okay? So material A and B, okay, when temperature decreases, actually B shrinks more in this case than A, so then it bend this metal strip in this guy, in this side, okay, towards the B side. So then it moved it in that side, okay. So the needle will move accordingly. Now, as I mentioned, material will expand in one dimension. It will also expand in a second dimension. So if you have a thin sheet or piece of paper, if temperature changes, then it's also going to be either expand or shrink accordingly. So temperature increases, resulting in the material being expanding. And then when it decreases, the material will actually shrink. Okay. Now, if there's an opening inside there, so then it will do the same. Okay. So temperature increases, the hole will actually expand. Then temperature decreases, the hole actually will shrink. Okay. And then also for 3-dimensional, it's the same case. If temperature increases, it will also increase in 3-dimensional. The volume then will actually increase. So in this case, the expansion in vertical direction and horizontal direction will result in the increase of the area in total. So then we will say there's an area increase. In this case, there's a volume increase. Okay. So let's take a look at the 2-dimensional expansion as an example. And then we can kind of start from there and then predict what will happen for the 3-dimensional, okay? So this is the result. For 2-dimensional expansion, the increase in area, delta A for area, is approximately twice of linear expansion coefficient times the original area times delta E, the change in temperature, okay? So let's take a look on the algebra here. We are, for the simplicity, we are going to just assuming this is a square sheet materials. Okay, let's take a look here. Let's say this is a square sheet with the size being L. type in L. And let's say if there's a temperature increase of delta T, so then, yeah, this is L, and then this is also L. So then vertically, this guy will expand by delta L. Okay, so this is delta L. Horizontally, it will expand also in with delta L. Now I'm going to say I actually fixing this sheet at this point, so it's expanding in that direction, right? If it's not fixed, then you'll actually expand in both directions, right? So this way and that way. After the temperature increase of delta T, all right? So then this will be your new area. A new area, A prime, will be actually L plus delta L, right? And square it. Your original area will be A, right? That will be just L squared. So the change in area, that should be A prime minus A, which is this one minus this, right? So if you expand this guy, this is A plus B squared, right? Equals to A squared, L squared plus 2AB, A times delta L squared, right? So you can actually get 3 terms, L squared plus 2 times L delta L plus delta L squared. So then delta A prime, so here A prime minus A, so this minus that, right? So then resulting, because this and this will cancel, resulting in just 2L times delta L plus delta L squared, okay? Now, delta L, if you remember, this is equal to, for one-dimensional expansion, either horizontally or vertically, right? This is equal to alpha times delta T, right? And then alpha is typically in the tens of -6 order, right? So this is a very small number. So let's take a look at our changing A. It's 2 times of L times alpha times L times delta T, right? Plus delta L squared, that means this guy squared. So plus alpha squared, L squared times delta T squared, right? So alpha is on the order of 10 to the -6. So the first term has alpha here. And this is L and L squared, right? And delta T. So typically the change in temperature may be in 10 degrees, 20 degrees, whatever, right? It's still much smaller or if you do like 100 degrees even, right? So that's 10 to the 2, right? So it will still not be able to cancel out this 10 to the -6, 2 times of that square, right? So this term compared to this term will be at least thousands smaller than this guy, right? So then you can actually ignore this higher order, right? Just ignore that guy. So then delta A is going to be approximately equal to 2 times alpha, right? And so you can put alpha in front, and then L times L, so L squared, and then times delta T. Now alpha or L squared is 8, right? And this is equal to, this is approximately equal to, delta A is approximately equal to 2 times alpha and then A delta T, which is the result shown on the PowerPoint slide. Okay, so you start with a square and then expanding horizontally and then vertically. And then you do the difference of the area after expansion and then before expansion, right? The two, one subtract off from the other one. So then you get this 3 turns minus 1 turn, you get 2 turns. So then delta L, originally change of length in one dimensional will be alpha times L times delta T. So then this guy, you take delta L as that, substitution there and there, you got this, okay? And then ignore the higher orders, smaller terms, you get this guy, which is this one, Okay, so that's how you actually get this as your conclusion. So let's go back to the slide. All right. So we have shown that delta A is approximately twice of alpha times A times delta T. So this is for two-dimensional expansion. Now the same will happen to three-dimensional expansion. We probably can see that. So for three-dimensional expansion, delta V is going to be equal to approximately equal to 3 times of alpha, right? Times original V times delta T. So if we call 3 times of alpha, a name to it, we call it beta. So beta is equal to 3 times alpha. So then we get this change in volume equal to beta times original volume times delta T, the change in temperature, where beta is equal to 3 times alpha. Okay. Again, this is called then the coefficient of volume expansion. So we only highlight the coefficient of linear expansion and coefficient of volume 3D expansion, which we use alpha and beta respectively. Okay, and coefficient of volume expansion has a SI unit, again the same as alpha, Kelvin inverse or Celsius degree Celsius inverse. Okay, so that's thermal expansion in 3 dimensions. Now I did mention there's an expansion exception. So water is one of the exception. When temperature increases, a very small region of it from 0 degrees Celsius to about 4 degrees Celsius. Actually, when temperature increases, the density increases, which means the volume actually decreases. All right, so this is one exception. After that, it's normal. When the temperature increases, actually the volume increases, so the density decreases. So this is a curve of density versus temperature. Okay, so you have to think about that. Density and volume are inversely proportional to each other. If density increases, that means that for the same amount of the water, actually its volume will decrease. All right. Okay. Now it's winter, so because temperature drops quickly and sometimes it rises up to a larger extent. So you see this potholes because of the concrete being stretched, expanded, and compressed often. So then it happens, okay? So it actually breaks down, so you see those potholes. In winter, if your car's tank is on low, because temperature is low, actually means volume is actually smaller, okay? So all the density actually is larger in that sense. So you actually, for the same indication on your tank, past or your tank, you might be able to go a little bit further just because then the density is smaller. It's actually higher when temperature is low for the gasoline. Okay, so you actually have more gasoline in terms of the mass, and then its molecular number of molecules. All right. So at the end, let's take a look at one example here on volume expansion. So it says early in the morning when temperature is 5.5 degrees Celsius, gasoline is pumped into a car's 53 liters steel gas tank until it fills to the top. Later in the day, the temperature rises to 27 degrees Celsius. Since the volume of gasoline increases more for the given temperature increase than the volume of the steel tank, gasoline will spill out of the tank. How much gasoline spill out of the tank? And coefficient of expansions are given linear and also as volume expansion. Okay, so there are two materials involved: iron as the steel, which has the linear expansion coefficient 12 times 10 to the minus 6, gasoline 0.95 times 10 to the minus 3. All right. So I will take down the notes here. So it says initial temperature, right? In the morning, that's the initial temperature, 5.5 degrees Celsius. Final temperature later in the day, 27 degrees Celsius. And the volume, initial volume, is 53 liters, both for the tank and gasoline. We'll just ignore the steel tanks because it should be thin, right? Okay. All right. So it's asking you how much spill is it? Let me show it on my paper here. You're looking for V spill. So you can imagine there's a tank, right? And then there's gasoline inside. Now the tank probably just expand a little bit. So maybe a little bit tank, maybe not at all. So this is the tank. However, the gasoline will expand more than the tank. So maybe expand by this much, right? This is gasoline. So you'll see more gasoline will expand it than or the gasoline expand more than the tank. So delta V of the gasoline, so we can calculate delta V of the gas, right? That will be, according to the equation, will be beta, right? Times V original times delta T, okay? And then also for delta V of the tank, it will be also beta. Now this is gas, okay? Gas, this is tank, V delta T. So it gives us that, you can check your PowerPoint slide. It gives us that for iron, the steel, the tank, right? It gives us 12 times 10 to the minus 6 Kelvins inverse. Be careful, okay? So it actually gives you alpha equal to that, right? Beta should be equal to 3 times alpha, okay? So remember that. If you are given alpha and then you need beta, you have to do 3 times of alpha. All right. So beta of tank then is 3 times of alpha tank. Okay. Now beta of gasoline actually is given. So 0.95 times 10 to the minus 3 Kelvins inverse. Okay. Delta T will be the same for gasoline and tank. Okay. So delta T will be 27 degrees minus 5.5 degrees Celsius. That gives you 21.5 degrees Celsius. Okay. And remember, degree Celsius and degree Fahrenheit, they are the same if the increment are the same, right? So if there's a difference of 21.5 degrees in Celsius, that's also 21.5 degrees in Kelvin, right? So then if you realize that you don't have to convert those two numbers in Kelvin first and then do the difference, because you pretty much will add 1 by 2273.15, right? And also the other one by that, right? And then you subtract one of another. So it will be the same, basically. All right. Okay. Now the initial volume of the two will be the same. Both are 53 liters. Okay. So then the spill of the gasoline, V spill, it should be equal to the expand amount of the gasoline, right? Minus the expand amount of the tank. So then this will give you beta of gas, V delta T, minus beta of tank, V delta T. All right, V delta T and V delta T are the same. So it basically will be just doing beta of gasoline minus beta of tank times V times delta T. All right. Now, beta of gasoline will be 0.95 times 10 to the minus 3 Kelvin inverse. minus beta tank. So this is this thing you need to multiply by 3. 3 times 12 times 10 to the minus 6 Kelvin inverse, right? Times 53 liters times delta T, which would be delta T will be 21.5 kelvins. Okay. So then at the end, you'll get about 1.04 liters of gasoline. So that means, right, if you fill your gas tank in the morning when the temperature is low, you actually get a little bit more gasolines than if you would fill your tank later in the day. Okay, so you learn something today that you can apply to your daily life and save you some money immediately. All right. So I will see you again in the next lecture. Bye. Have a good day, guys.